Okay, so we're going to spend the next little bit of time doing a mini unit here, about a week here, on vectors and linearization. So we're going to dive a little bit deeper into vectors and actually start doing some math with vectors. And we're also going to talk about a technique for analyzing graphs called linearization. Last unit, you folks got a little bit of an introduction into vectors. We talked about how vectors are numbers that have a direction associated with them, and things like velocity and acceleration and displacement are all vectors because they all have a direction. But so far, at least mathematically so far, we've only dealt with vectors that are purely horizontal or purely vertical. Obviously, things are not restricted to that, right? Cars can travel in directions other than just northeast, south, and west. They could travel northeast or southwest or a lot of different possible directions. So we want to be able to analyze vectors that are at angles, that are not purely horizontal or purely vertical. And this is going to help us as we transition into our next unit, which is forces. So here we have a grid with 2 points marked out, point 1 and point 2. And we're going to pretend that this is kind of like an overhead map here of some location. And a person is actually going to move from point 1 here up to point 2. Let's think for a second about what our displacement would be if we took that trip from point 1 to point 2. And we're going to draw a vector representing that displacement. So our vector representing that displacement would go from point 1 directly to point 2 and point in that direction. That would be our displacement as we move from 1 to 2. Okay, now suppose that instead of just drawing that displacement vector, pretend that this is actually a map of Philadelphia, right? Philadelphia is laid out like a grid, thanks to Benjamin Franklin and some others. So this is kind of like an overhead view of some of the streets in Philadelphia. And let's say that we're here at point 1 and we want to walk to here at point 2. Well, how would you walk from point 1 to point 2? You can't obviously take this direct path because there's buildings and other things in the way. So probably what you would do is you would walk 6 blocks to the right or east and then 6 blocks up. You also could go north or up first and then east. It doesn't really matter the order, but let's just, for the sake of this problem, say we go east and then north. That would take us from point 1 to point 2. Okay? Our displacement, however, would still be this direct line connecting the two, right? Our displacement is how far we are from where we started. But we wouldn't walk that actual path. We would walk along this street 6 blocks and then up 6 blocks. It's important to note, though, that these two pathways, our direct line, okay, assuming we could potentially walk that, and our path where we go east and then north, they result in the same final position. Okay, they result in the same overall displacement as well. So in some ways, this blue path is equivalent to that black path. Obviously, this is a shorter distance, but in terms of the displacement and in terms of where we end up, it's equivalent. Okay, so these two mathematically are equivalent. So as we just said in the previous slide, if we're walking along that path from 1 to 2, we have a few options. Okay, we can either walk directly from 1 to 2 along that black path shown, or we can walk some distance east and some distance north. All right, and what we're really doing there is we're introducing the idea of vector components. Okay, instead of walking at an angle, we're breaking it down into walking some amount east-west horizontally and some amount north-south vertically. And we end up with the same result. We end up with the same overall displacement. We're going to talk a lot about displacement here in the beginning of this unit. But this would apply to any vector. It doesn't necessarily have to be displacement. But we're going to end up with the same result. And so what we did, like I said, is we did our vector components. We found an x component and a y component. And what that really does is it represents, all right, the amount of the vector that points in the x direction or the y direction. Okay, so let's say we walked a distance of 100 meters at this angle here, right? This x vector component tells us when we walk that 100 meters, how far did we go east? and how far did we go north in that period of time. Okay, so maybe let's say this is a 45-degree angle. Okay, and that would mean that when we walk 100 meters at that angle, we travel 70.7 meters east, where we end up 70.7 meters east of where we were, and we end up 70.7 meters north of where we were. These guys here would be the vector components. And the reason why we're introducing all this, the reason why we're even talking about this, is you're going to find moving forward it is much, much easier to deal with vector components instead of angled vectors. Right, they're going to make your life a lot easier to work with, and in some cases they're going to make problems possible to solve that otherwise would be impossible to solve. Okay, so let's talk a little bit more about vector components. The first thing we're going to talk about is how exactly to draw these vector components. Okay, and I always think back when we're drawing them to that walking in the city example. Okay, thinking about how you could walk from one point to another only by going east-west and north-south. So what we're going to do is, when we have a vector at an angle like this, okay, so when we're drawing our vector, we're always going to start here at the tail of our vector, at the beginning, we call that the tail, and we're going to draw our first component. I usually draw the horizontal component first, but you certainly are welcome to draw the vertical component, as you see here. Okay, and so we're going to draw that first component showing how much we go horizontally, or how much of that vector is vertical. And then from the end of that first component, we're going to draw our second component. Okay, draw the vertical or the horizontal, depending on which one we haven't drawn yet. So one really important thing to notice when we're drawing these is vectors should always be drawn tip to tail. Okay, and so what I mean by that is we're looking at this intersection point where our two components intersect. All right, and after we've drawn that first component, we're always going to draw that second component from the tip of the first component, the arrowhead there. We're going to put the tail of the second component and go from there. All right, so we draw a horizontal one. From the end of our horizontal one, we draw our vertical one. Or we draw our vertical one, and from the end of our vertical one, we draw our horizontal one. And they always line up tip to tail. So that's one thing we want to keep in mind. Second, we always want to make sure that these components are perpendicular. Okay, we're always breaking it into horizontal and vertical, so our two components should always be perpendicular. And lastly, we want to make sure that the direction of the hypotenuse of that overall vector matches the directions of our component. So this vector is going to the right and up, which means we have a right component and an up component. No matter how we draw it, we need a right component and an up component. So we have a few examples here of ones that are not drawn correctly. The first one here, we see that our vector is going down and to the left, but our components go right and up. So that doesn't match, that doesn't work. Okay. We have another bad example here. This vector is going up and to the left, and we see our one component goes up, so that's good, but our other component goes to the right. All right. This also shows how they're not lined up tip to tail. That would be tip to tip. Okay, we don't want that. Lastly, this vector goes up and to the left, and we have an up component, which again is okay, but another right component. And we look at how they're lined up tail to tail, and that's not good either. All right, so all of those are not good. We want our vector components to look like these examples here. So we have a little practice here, so pause the video for a second, take a stab at this and try and draw the x and y components for those three vectors at an angle. Okay, so let's go ahead and go over this. So I'm going to start with this vector here, which is going up and to the right, which means I'm going to draw a component to the right. And from the end of that, I'm going to draw a component going up. We could have switched them around, so if you had gone up first and then to the right, that also would have worked. Moving on to this one, which is up and to the left, I'm going to draw one component to the left and then a second one up. And once again, if you flip the order of those and went up first and then left, that would also work. And then this final vector here is down and to the left. And so I'm going to go ahead and draw my components. We have one going to the left, one going down. And again, if we switched them, went down first and then to the left, that would work as well. So you don't need to draw that entire rectangle, either the blue or the red is sufficient. The next thing we want to talk about is naming vectors. So when we get into these vectors in 2 dimensions, there's 2 ways that we can describe them. Okay, we can either talk about our vector components, right, and actually name them based off of our components. So for example, for this situation here, we have 4 meters to the right and 8 meters up, or 5 meters per second west and 7 meters per second south. So giving both those x and y components is sufficient to describe the vector. Just like with our city blocks, we could have said 6 blocks east and 6 blocks north, and that is enough direction to get the person from where they started to where they want to go. All right, we don't need to necessarily know the actual distance from one point to another, or the angle, the heading we sometimes call it. We just need to know the 2 components, and that is sufficient. The other way that we can name it is without the 2 components, we can give the actual distance and give the heading. Okay, so in this case, we're going to give the magnitude of the vector, right, which is the hypotenuse, and that's an important point. All right, we've talked about magnitude before. That's just the amount. So when we're dealing with 2-dimensional vectors in these diagrams here, the magnitude is simply the hypotenuse, just the amount of that vector. And then we can also give the direction, which in this case, what we really mean by that specifically is the angle, is the heading. Okay, so we have this vector down here. And we would say that this vector is 8 meters. All right, so that's the magnitude, and the direction is 25 degrees north of east. Okay, so what does that mean? When we say north of east, we're starting with our east direction, okay, and we're going 25 degrees north of that east direction. So there's our 25-degree angle. We're starting with east and going 25 degrees north. All right, and that's what ultimately gives our heading. So that's what that means. That's how we're going to use that directional component to this. All right, we have another example here, 10 meters per second. That's our magnitude, the hypotenuse, and the angle is 15 degrees east of north. So we're starting with the north direction here, and we're going 15 degrees east of that north direction. All right, and that ultimately gives us our heading. Okay, and lastly, we have 6 meters at an angle of 40 degrees south of west. So we're starting with our west direction, okay, and we're going 40 degrees south from that initial west direction. So 6 meters at an angle of 40 degrees south of west. So that's the other way we can name our vectors. Just a quick reminder here of something that dates back actually to our math pretest, but keep in mind that when we're drawing these vectors, they'll always be perpendicular. They'll always form a right triangle. So good old SOHCAHTOA and the Pythagorean theorem are going to be very much in play here, and we're going to use them as we're analyzing some of these problems.